So as we now study the change in direction, it leads to what's called Snell's law. And we're going to try and put a formula to the changes in direction that we met at National 5. We're using for this a semicircular block, and the reason for that, remember that if you strike exactly the midpoint of the flat side, then this is the centre of a circle. And therefore that line there is along a radius of a circle, and that will always strike the curved edge of a circle at right angles, which means you get no change in direction. You do still get refraction, you do still get a change in speed, but you get no change in direction, which makes it much easier to do the measurements. So that's why we tend to use these semicircular blocks. So at the curved surface, there's no change in direction. In this example, the refractive index of the glass is 1.5, and we then measure the angles from the normal. So the normal, remember, is defined as a line at 90 degrees to the surface at the point where the ray meets. We're only looking at the change in direction here at the flat surface rather than the curved surface. So this is our angle of incidence, which is called θ1, and this is our angle of refraction, θ2. And as it enters the medium, it bends towards the normal. That's what you learnt at Nat 5. But what we can actually find is that there's a precise relationship for that. I can change it to different angles, and you can see that the angle is always less in the medium than it is in the air. And the relationship that we find then is n equals sine θ1 divided by sine θ2. And just like the formula for speed we saw on the previous slide, θ1 is always in air, θ2 is in the medium. So it doesn't matter whether you're going from air to the medium or medium to air, the formula is always the same way around. And it's called Snell's law and defines the refractive index of the material. And you can try that at different angles and check that out. We can also change the refractive index in this simulation. So we make that 1.2. And if we had different refractive indices, then the amount of bending will change. Okay, for the same value of θ1, you'll get different values of θ2. And basically a higher refractive index means you get a bigger change in direction, which means the angle of incidence, the angle of refraction will be even smaller. Now, if we reverse the direction of the ray there, and start the right hand side and go that, the formula, the values all stay exactly the same, and the formula stays the same. So that would still be θ2, the angle in the medium would be 19.7, and the angle in the air would be 30.5. There's always the angle in the air on the top.